Hello. Today's focus is prediction problem-based learning, and we're going to take a look at Markov decision processes. I'm Dr. Coates. Let's start with the why. Why should you learn something about AI and MDPs? Well, because AI is going to transform the healthcare space and will likely displace many of us. Now, doctors can maintain a role in the new AI economy by being part of the explainability chain. If the developers can explain their products to us, to our satisfaction, we can then explain their products to our patients. Now, Markov decision processes are an old mathematical idea which has found new and marvelous applications. In AI, it's a decision framework which is the basis for many reinforcement learning models. Now, these are AI approaches where the AI learns on the job using rewards and costs of taking an action to inform the next action. These next best action models can be seen in predictive text, turn-based games, speech recognition software, simulated user behavior, etc. To gain some familiarity with MDPs, I'd like to tell you a little bit of a story about the Markovs. Let's meet the Markovs. Here are three generations of doctors. Professor Markov, who is 80, Dr. Markov, who is now 53, and Miss Markov, 28. When Professor Markov was a young man, he dreamed of being a consultant vascular surgeon. Now, becoming a surgeon was not easy. There was a game, and you had to play it. There was a path that one had to tread, the right schools, the right grades, the right hospital placements, but the pathway was well determined. One step led to another in a chain, which we can call a Markov chain. In this simple chain, getting to B was entirely dependent on step A and step A alone. At each step, taking action led to a reward. For example, if you passed your exams, you moved from SHO to registrar with a new title and higher pay. However, success was not guaranteed. For example, if you took an exam, there was likely a 70% pass rate. This we can call the transition probability. Elements so far. One is declaring a state change. Two is describing the actions needed to achieve this state change. And three, asserting the probability of this outcome or the reward of this outcome. To summarize, for a series of random but countable variables x, the probability of moving transition to the next state depends on the present state only. This is known as a Markov property. This chain is memoryless, with each transition depending only on the last state and the last state alone. For each state action coupling, the transition probability of achieving the next step is quantifiable and is a number between 0 and 1. So now we can formalize a policy. For example, we might only take actions which lead to a reward or a high chance of success. So Professor Markov comes up with a clever way of summarizing the change in state along the chain. He uses a grid or a matrix. Now, as these were simpler times, for him the probability of moving from A to B is 1. However, the probability of moving from A to D is 0. Notice that each row adds up to 1. As the matrix contains transition probabilities, we can call this matrix a transition matrix. Like other matrices in maths, other laws of matrix algebra apply, which really does come in handy and explains why Markov decision processes are such a versatile tool for making predictions. Fast forward a few years hence, and the first in the line of Markov doctors is now a consultant vascular surgeon. Indeed, his policy of steps A through E has worked really well, and he is now a professor. His son, Dr. Markov, has finished medical school. Professor Markov would dearly love for his son to follow in his footsteps. He believes he can grandfather his son into vascular surgery and shares his deterministic policy for success. Secretly, his son, Dr. Markov, doesn't really want to be a vascular surgeon. The sights, sounds, and smells of the operating theatre leave him feeling quite ill. He'd like to have time for his hobbies, which include cycling, swimming, and bell ringing. Furthermore, the training environment has changed quite a bit since Professor Markov was a young junior. These changes can be summarized as the Kalman epoch. Kalman reviewed medical training and practice and published a report in 1997, which was a blueprint for perhaps a more transparent and fairer training process. Post-Kalman, medical training had minimum training periods and defined pathways. Your fate was not determined by following the right steps and knowing the right people. Instead, there were now more factors at play. Professor Markov can't just set young Dr. Markov on the right track with his inherited policy. The new training environment means that it is no longer guaranteed that Dr. Markov will end up in vascular surgery and faces a more uncertain future. Dr. Markov also really values his free time. So for Dr. Markov, the optimal policy will be one that achieves the ultimate reward of a consultant career, but minimizes the cost of training time. In this new training environment, we have moved away from first-order Markov effects, where getting to E only depended on D. Now we have second and third order Markov effects where performance at stages A, B, C, and D can feed forward into getting to step E. Professor Markov could fill up an easy transition matrix of zeros and ones. However, for young Dr. Markov, the transition matrix is far more complicated. Each row still adds up to 0, but for each state there are several more possible outcomes that he knows of. The jumps between states are also less intuitive. Importantly, when setting up an unsupervised learning algorithm using reinforcement learning, this foundational step is where the thinking really takes place. The matrix has to adequately capture all possibilities and estimate rewards and costs correctly. If the matrix is wrong, the model will fail. This is why domain experts like you are needed, even at this early stage, to improve insights about the very parameters underlying the models. Back to Markov. He now has to draw up a chain with all the different options. He attempts to fully observe the training environment. Now, being mathematically minded and not wanting to disappoint his father, he decides to amend his father's policy, but in a passionless and systematic way. Dr. Markov comes up with a formula. He realizes that it is possible to calculate the value of each chain of events based on the cumulative reward that the chain delivers. Remember too that Dr. Markov values his free time. Therefore, he needs to factor in the cost of time against the rewards of training. So he introduces a new parameter. This is gamma, a discounting factor. It applies a discount to the reward of the new state in recognition of the cost it took to get there. So, for example, entry into specialist training may take 6 years. So the reward at entry is discounted by a standardized factor of 6 in recognition of the time cost. Dr. Markov has used his father's matrix idea to map out the possible steps. He has then used his formula to estimate the maximum cumulative reward of each chain and factor in costs of training. So Dr. Markov not only has a new and objective policy, but a real number that he can use to measure the value of one training chain against another. He finds that the career chain that optimizes his values leads to interventional radiology. Now Markov decides that his equation is just too good to languish in his notebook. He sends it into a mathematical journal for publication under a pseudonym, Bellman. Get it? He enjoys Bellman. Bellman. Fast forward 30 years, and we are in the present. It's the epoch of Miss Markov, the professor's granddaughter, and the doctor's daughter. Dr. Markov is now a consultant interventional radiologist. Interventional radiologists like Dr. Markov have put vascular surgeons like Professor Markov out of work. However, Miss Markov has just done her MRCS and she's not sure what surgical specialty she wants to pursue. Her mentor suggests that she choose life and has advised her to go to Australia for a few years and do whatever specialty that allows you to spend your weekends on Bondi Beach. So that's a hand-me-down policy from her advisor that she could follow. However, she is familiar with her grandfather's matrix and has read her father's Bellman paper. So instead of implementing her mentor's policy advice, she decides to use these tools to objectively identify a new good policy. Since her father was a junior, however, there have been even more changes. The government has modernized medical careers with some interesting results. There are now multiple entry points to training. Not all journeys start at A. Sometimes experience helps, but sometimes it counts against you. So rewards can now be negative. Boss patronage matters even less now. To take a decision about Australia, she would need to simulate lots of training chains, some with Australia factored in, some without, etc. Now she begins this brute force approach and runs hundreds of potential Australia scenarios. However, soon after she starts, she realizes that the system is now too complex and too random or stochastic, and she cannot adequately capture all the complexity and parameters and estimate all the rewards. Just as she is about to give up, she has a stroke of luck. Her boyfriend, who has left medicine to become a data journalist, discovers a secret GMC database. This database contains details of all UK doctors who have gone to Australia in the last 80 years. This transition from the UK to Australia happens at different career stages. Interestingly, there is evidence that 50% of emigres to Australia come back. So now she can use her grandfather's matrix to map changes of state from the UK to Australia. The database also captures information about hospital rotations from qualification to consultancy. So she can use her grandfather's matrix to map out a second transitional matrix which contains probabilities of moving between rotations till consultancy. Now, all in all, she has thousands of training chains. Like all random data, however, she starts to notice some patterns. The data converge, meaning that some chains are more probable than others. She realizes that she can take a Monte Carlo approach to use random sampling of these stochastic data to estimate likely probability distributions. What we have here is a hidden Markov environment. Some parameters are observable and some are not. However, Miss Markov now has two matrices describing transitional probabilities for both visible and hidden parameters. She can now assume Markov properties to solve for the chain. For example, she could find the most probable chain to deliver a short early career in the UK and a long later career in Australia thereafter. The generational differences in the Markov environments usefully illustrates the challenges of applying models in the wild, and here it is appropriate to raise the spectre of Karl Rove. Within stochastic environments, there can be many known unknowns and unknown unknowns. We can see that unlike Professor Markov, who could make deterministic policies, Miss Markov's data environment is less favorable. In healthcare, we often work with hidden Markov scenarios. Consider, for example, a 56-year-old living with obesity. We observe the weight transitions. However, specific chains of genetic, epigenetic, environmental, and psychological events have led to this moment, and they are often obscure. We have some chain information, but not all. So why the long story? Well, firstly, it's really important for us as clinicians to understand that AI is based on old ideas finding new applications. And yes, I have taken some liberties telling the Markov story. Markov was actually a famous Russian mathematician who lived in the 20th century and is credited with key insights in approaching stochastic problems. Richard E. Bellman was a talented American mathematician who made significant contributions to applied mathematics, particularly in the creation of dynamic programming. He also coined the phrase the curse of dimensionality, which is a whole other fascinating topic for another day. Familiarity with Markov chains matters when we think about reinforcement learning and how AI prediction might affect our patients. Firstly, if the transition matrices set up are garbage values for rewards and costs, then it follows that we will churn out garbage outcomes. Secondly, with increases in complexity of modeled environments, we need to consider known and unknown parameters. Not everything is amenable to observation. Thirdly, the multidimensional and seemingly random environments we operate in within the healthcare space actually present incredible avenues for applying stochastic methods. So instead of trying to reduce parameters within our models to coerce all our information into spreadsheets that we have been taught to handle, we should embrace AI and use that to solve the problems before us. Lastly, it's important to think about Professor Markov's feelings. He wanted his son to be a vascular surgeon. So although Dr. Markov's formula delivered an accurate method of predicting what is the best chain of events to follow, it wasn't what was desired as an outcome. Similarly, one might invest in a Q-learner AI that accurately predicts the likelihood of having lung cancer based on key life events and environmental exposures. The aim of this AI agent is to reduce GP attendances to just high-risk patients. However, Mrs. Jones doesn't want an app to text her with a 10% risk of lung cancer. No, Mrs. Jones will only believe the GP who listened to her chest and squeezed her hand in reassurance. Which brings us back to our explainability challenge. Although these reinforcement learning models can be useful and accurate, they still require human input to modify human behavior. The accuracy of predictions is perceived to be just as important as trust and accountability. So let's think about the lingo before we finish up here. When you're thinking about Markov models, you're going to hear a lot about SARSA, MCMC, DQN, reinforce, Q-learning, PPO. All of these are variations on a theme, depending on how time is handled, the knownness of the data environment, how the probabilities between state changes are handled, etc. This is a testament to just how versatile Markov decision processes are as a tool within the computing field. So when faced with a healthcare AI that predicts next best action using MDP, here are some questions you might want to ask. The top question is always, show me your data. We can also query the involvement of domain experts in development. With our knowledge of the stochastic environments in healthcare, we ought to find out what argument the MDP is optimized for. Maximum quality of life, maximum length of life, minimum financial cost, and if cost, whose? The consumer or the healthcare organization? Lastly, how well do state action chains map to lived experience? To conclude, I remember the early days of ambient AI dictation. Every time I said Hirschsprungs, the app would type out hairsprings. If I failed to recheck the dictation app's work, I would sometimes get a letter from a rather perplexed GP asking me to explain this new hairsprings diagnosis. Now, ambient dictation has been on a journey of improvement. Importantly, it has progressed through a reiterative interaction with domain experts like you and me. We as doctors can choose positive engagement and help clinical AI tools be the best version of themselves. Our patient safety depends on it. Please send suggestions for videos in the comment section, and we'd love it if you'd share this video with at least one medic friend.